Assalamu alaikum and good morning, everyone. Thank you for joining me today. My name is Ahmad Hafiz bin Matsam, and I'm here to present my research on the investigation of the effects of air intake temperature and humidity on the volumetric efficiency of a single-cylinder spark ignition engine. This study was conducted at University Technology Mara, College of Engineering, where we aim to gain insights that could potentially enhance engine performance by optimizing these environmental factors. Let's start with a brief introduction to the study. As we know, there is an increasing demand for energy-efficient internal combustion engines, particularly in reducing emissions while maintaining high performance. Volumetric efficiency, which measures the engine's ability to intake air, is crucial for engine performance. However, this efficiency is influenced by various factors, including air intake temperature and humidity. Our study aims to explore these effects in detail, with the goal of optimizing volumetric efficiency in spark ignition engines. Existing research has shown that higher air intake temperatures generally decrease volumetric efficiency by reducing air density, while increased humidity tends to improve efficiency by aiding charge cooling. However, most studies have focused on the individual effects of temperature and humidity. There is a noticeable gap in the research regarding their combined effects, particularly in single-cylinder spark ignition engines, which is the focus of our study. This brings us to the research gap. While numerous studies have explored the individual impacts of temperature and humidity on engine performance, comprehensive research that considers their combined effects is lacking. Additionally, the focus on single-cylinder engines is limited. Our study aims to fill this gap by investigating how both factors together influence volumetric efficiency, thereby contributing valuable insights that could lead to better engine optimization strategies. To address these gaps, we employed a one-dimensional engine simulation model to analyze the fluid dynamics and thermal characteristics under various conditions. The study focused on engine speed, air intake temperature, and humidity as key parameters. We calibrated our baseline engine model using data from Mariucci, 2006, and conducted a full factorial design of experiments, with 75 runs. The results were further optimized using the Global Response Surface Methodology, or GRSM, to ensure accurate findings. Below is the one-dimensional simulation setup model. In this slide, we explore the design of our experiment. The parameters tested included engine speeds ranging from 2,500 to 4,500 RPM, air intake temperatures from 26 degrees C to 34 degrees C, and humidity levels between 68% and 92%. We used a full factorial design to evaluate volumetric efficiency across different parameter settings. This comprehensive approach allowed us to understand the individual and combined effects of these variables on engine performance. Here, I'd like to highlight the specifications of the single-cylinder engine used in our study. This table shows the key parameters, including engine bore, stroke, compression ratio, and valve timings, among others. We validated our simulation model against the calibration data to ensure that the model accurately reflected real-world engine performance. The calibration results demonstrated good agreement, confirming the reliability of our simulation approach. Moving on to the results, our linear effect analysis showed a clear positive correlation between engine speed and volumetric efficiency, meaning that as the engine speed increased, so did the volumetric efficiency. We also observed a slight negative correlation between air intake temperature and volumetric efficiency, indicating that higher temperatures slightly reduced efficiency. Interestingly, within the tested range, humidity had a negligible impact on efficiency. The line graph here illustrates these trends. To delve deeper, we conducted an analysis of variance, or ANOVA, which confirmed that engine speed and air intake temperature significantly impact volumetric efficiency. However, the effect of humidity was found to be statistically insignificant in this context. The regression equation shown here captures the relationship between these parameters and volumetric efficiency, providing a mathematical model for predicting engine performance under different conditions. This slide presents the response surface analysis, which visually depicts the interactions between variables. For example, in the first plot, we see how engine speed and temperature interact at a constant humidity level of 80%. The second plot examines the interaction between engine speed and humidity at a fixed temperature of 30 degrees C. These plots highlight how the combined effects of these variables influence volumetric efficiency. offering deeper insights into optimal engine operation conditions. Based on our analysis, we identified the optimal configuration for achieving maximum volumetric efficiency. The best result, a volumetric efficiency of 0.97, was achieved at an engine speed of 4,500 rpm, with an air intake temperature of 26 degrees C and 68% humidity. These findings underline the importance of precisely controlling engine speed and air intake conditions to optimize performance. By targeting these specific conditions, we can enhance engine efficiency significantly. To summarize our findings, engine speed emerged as the most critical factor influencing volumetric efficiency, followed by air intake temperature. While humidity's effect was minor, it shouldn't be completely disregarded, especially in certain operating conditions. These insights suggest that strategies such as intercooling, which reduces intake air temperature, could be beneficial in improving engine performance. The findings also open avenues for further research into how varying engine configurations might influence the role of humidity. In conclusion, our study successfully investigated the combined effects of air intake temperature and humidity on volumetric efficiency in a single-cylinder spark ignition engine. We found that while engine speed and temperature have significant impacts, humidity plays a relatively minor role. However, understanding these effects is crucial for optimizing engine performance. For future research, we suggest a deeper exploration of how different engine configurations might alter these dynamics and further improve volumetric efficiency.